Hello, in this course we will use two kinds of mathematical objects, scalars and vectors. A scalar is just a number, it only has a value, which is expressed in some physical units. A vector also has a value, but it also has a direction. We can define a vector as a product of its value and a unit vector, which has a value of 1 and points in the direction of the vector. We will use this notation often in this course. This unit vector can be found by dividing the vector by its value. This is true irrespective of the coordinate system used. Any vector can be represented as a sum of its components. Those components will depend on particular coordinate system used. Remember that the vector itself does not depend on a coordinate system, but its representation in terms of components does. We can add and subtract two vectors. If those vectors are given by their components, for example, in the Cartesian coordinate system, the components of the sum or difference will be given by a sum or difference of corresponding components like so. We can also multiply a vector and a scalar. Components of such product will be products of the scalar and components of the vector. You can also multiply one vector by another vector. There are two different ways of doing it. One is called the dot product or scalar product. A dot product of two vectors is a scalar. Mathematically, dot product is a product of one vector's length by projection of another vector on the first one. It is therefore expressed as a product of the two lengths by the cosine of the angle between the vectors. In Cartesian coordinates, the dot product is simply given by the sum of products of corresponding components of the two vectors. Remember that the dot product of two vectors is only a scalar. It can be negative. That happens when the angle between the vectors is more than 90 degrees and cosine of that angle is negative. Another type of vector product is the cross product or vector product, because it is not a scalar but a vector. Geometrically, cross product is defined as a vector with length equal to the area of the parallelogram formed by the two vectors and with direction perpendicular to that parallelogram. Its direction is defined by the right-hand rule. You take your right hand, put your fingers along the first vector and then move them towards the second vector. Then your thumb will point in the direction of the cross product. The value of the cross product is given by product of the two vector lengths and the sine of the angle between them. Clearly, if you change the multiplication order in the cross product, its sign and direction will change to the opposite. In Cartesian coordinates, the cross product is given by the following determinant, which can be expanded into components as so. To describe electromagnetic quantities in three-dimensional space mathematically, we will need to use some coordinate system. In this course we will use three different coordinate systems. Let's briefly revisit them. The most commonly used is the Cartesian coordinate system. It is made of three mutually orthogonal axes, x, y and z. Any point in space can be represented by a vector which starts at the origin and ends at this point P. This vector can be represented as a sum of three vectors, each directed along one of the axes. The unit vectors corresponding to each direction are usually called I, j and k, or sometimes they are called a sub x, a sub y and a sub z. Alternatively, we can describe any point in 3D space using three perpendicular unit vectors, based on the cylinder. They are the radius of the cylinder r, the angle between the radius and the x-axis p and the vertical displacement from the origin z. In cylindrical coordinates, a vector can be represented as a sum of two vectors, one along the radius and another along the vertical axis. You can very simply express Cartesian coordinates in terms of cylindrical coordinates like so. The cylindrical coordinate system is most useful when the problem possesses the cylindrical symmetry, meaning that nothing is changed by rotation around the vertical symmetry axis by any angle. That is the case when we are dealing long-line charges, wires and currents. The last coordinate system we will use is the spherical coordinate system. Its unit vectors are based on a sphere. Each point is defined by 3 parameters, the distance from the origin r and 2 angles theta and p. The theta is the angle between the vector and the vertical axis. The p is the same as in the cylindrical system, the angle between the projection of the vector onto the horizontal xy plane and the x direction. You can also simply express the Cartesian coordinates x, y and z in terms of the spherical coordinated r, theta and p like so. The spherical coordinate system is the most useful with problems with spherical symmetry, when any rotation about the origin does not change anything. That happens for point charges or spherical charge distributions.